Okay, hello. Welcome back. So today we're going to see a different algorithm, a different machine learning algorithm, okay? We are going to work with decision trees. We are going to see step by step how we induce a decision tree, okay? From scratch. So, okay, consider this. Where is that pointer? I don't have that pointer anymore. And anyway, consider this data set, okay, is an illustrative data set. Okay, it's a data set made of movies. So you have each line is a movie, okay, and you have some characteristics of the movie. So the country, when the movie was made, okay, the star that was received by the movie, I don't know, some people that evaluate the movie, they give a star or no to the movie. And the genre of the movie, like science fiction, comedy, anyway, romance. And then our outcome is a categorical outcome. We want to know if the movie is going to make success or not, okay? So it's a very illustrative data set. So what we want to do is to induce a decision tree in this format, okay? So how do we define a decision tree? The internal nodes, they represent features. Okay, so decisions about a given feature. The edges, they represent the features itself, okay? And the leaf nodes represent target features, okay? So for example, I have a node that represents a feature, so country, then each edge represents a decision about that feature. So if the movie has a country value equals to USA, and then a star value equals to yes, then the movie will make success. Okay, we have success. Is it okay? So we construct this recursively, analyzing all these nodes. Remember yesterday in the end of the class that when I was talking to you.
But this is created with the this is created with the table that we are seeing before, or just it's
no,
just
it is related to the table.
It's related, but it's not with the data.
No, we are going to induce this decision tree based on that data.
Okay.
You mean this data? Yes. So this decision tree was induced using this data.
Okay.
And we are going to do this now. We are going to see. Okay. So, but we construct this decision tree recursively. First, we have to decide what feature is going to be the root of the tree. Question?
Yeah, so again, country is a feature.
Yes.
Like USA, Europe are edges. And what are these leaf nodes?
The leaf nodes are the decision, are the classes, the labels.
So true or false? Okay.
Yeah.
Thanks.
Okay. It could be a real number. For example, if I would like to predict, I don't know, the concentration of a given product, you know, or the production of a given, like I said yesterday, rice, species of rice. I want to predict the production of that rice. I can do this with a decision tree. Question?
It's just a comment. This seems like to me Phylogenetic tree is the same thing.
No. Well, I'm not really familiar with phylogenetic trees, but I mean, you have families, subfamilies, right, in a phylogenetic tree. Yeah, the idea is more or less the same. You have a tree, you have a root node, and then you go dividing your data. Yeah, the idea is more or less the same, okay? That's exactly the idea. So we get the whole data, and then we want to decide, okay, what's the best feature to be used to starting dividing our data according to the labels, to the outcome, okay? Then we do some statistics and decide, oh, the country feature is the best one. It divides our data. Then we have to get the subsets that resulted in the division after we apply the country feature. And then we have to decide again, okay, what's going to be the best feature to be used in a subset resulting from the division of using the feature country? Then we do some statistics again, and we decide how to divide the subset. So we go recursively dividing the set of instances, okay, our data set, until we find some subsets that we consider pure. That sometimes it's not, sometimes it's not totally pure, okay? But for example, I can divide my data until I get here to a leaf node where the majority of the examples belong to a given class. Okay, then we can stop dividing our data. We can think about some stopping criteria, but we are going to see this step by step. Okay, you can. Okay. So, a decision tree can be used to classify instances and also to predict a real value, okay, for a given instance. So I can classify in a categorical value, or I can predict a real number value, okay? So the objective is to classify here, in our example, the larger number of instances with the smallest possible tree. So remember when I told you about the trade-off bias variance? So we don't want a very huge tree, because a very huge tree will have a lot of nodes, like hundreds of nodes, and then the variance will be very high, and this tree will memorize data and will not be able to generalize to new data. We don't want that. So we want the smallest possible tree that is still good. It's still a good tree, okay? And so the algorithm to construct this tree recursively partition the training set until the sets obtained with the partitioning contain data, in our case here, that are from a single class. See? Okay. So let's start here. For example, let's think. If we select the feature country, so we have that whole data, all the instances and features, okay? If we select the feature country, okay, so we create a node called country. And because country, the feature country, has 3 possible values, USA, Europe, and others, then we create 3 branches that divide the data. Okay? And so if we look at our data, we can see that the countries, the movies that were made in USA are this one. The movies that were made in Europe are this one. And the movies that were made in other countries are this one. From the movies that were made in USA, 3 make success and 1 doesn't make. We know that because we know the label, okay? We know the outcome. The movies, if we get the movies that were made in Europe, 2 make success and 2 don't make success, okay? If the movies were made in another country, they will not make success at all, okay? So we are seeing here how this feature divides the data. And we can look at this division and see the quality of this division, okay? We can see the quality. So we can take a look at the quality. So let's see another feature. If we get another feature, for example, star. Okay, star has 2 values, yes and no. So it makes 2 divisions. It makes 2 subsets. If we choose the feature star to divide data, it results in 2 subsets. So if a movie has a star, okay, so these are the movies that have stars. And these are the movies that don't have stars. So from the movies that have stars, 4 make success and 3 don't make. From the movies that don't have stars, 1 have success and 2 don't. Okay, so it seems that this feature is a little bit better to divide the data than this one. Why? Because if we take this division, we can see here that we already have a decision on our data. Okay, we can look at our data and say, okay, if the movie was made in another country, it won't make success. So the class is null. So it's a pure division. We have instances here that belong to only one class, null. If we look at this division, you can see that most of the instances belong to the class success, and only one instance belongs to the class null. So it's an almost pure subset, okay? This is much better than this, okay? This is a terrible subset, see? Because if we look at the value of the feature country, we cannot make any decision. It would be like flipping a coin. We have 50% the chance of a movie makes success, and 50% of chance that a movie doesn't make success, okay? Looking at the data. Let's get the feature genre. Again, it's the same idea, okay? If we get the movies that are comedy, 4 of them make success, 2 don't make success. If a movie is about romance, it doesn't make success. If a movie is about science fiction, 2 don't make success, 1 makes success. Okay? So, how to decide what's the best feature? Which feature to select? So the feature to be selected must be the one that best separates the data of each class. We already know that. So for the feature country, I already told you, the value order has data only from one class. This is very good. It's a good division. The value USA has most of the data from class yes. Oh, that's good. Okay? The value Europe has equal number of instances from both classes. That's not good, because we cannot infer anything from that. Okay? So how to select a good feature? So statistics give us some measures to allow how to evaluate these previous situations. We have to use some statistics. We are going to use entropy, which measures the uncertainty of a random variable. In our case, a key quantifies to what extent the data are spread out over its possible values. Okay? So it's going to measure the quality of a subset. And after calculating entropy, we are going to calculate information gain. With information gain, we seek to reduce entropy. What means to reduce entropy? If we get a subset and we calculate the entropy value of this subset, low entropies will correspond to subsets where instances belong to only one class, very pure subsets. The higher the entropy, that means that the instances there are mixed. Okay? So, we are going to select the feature that offers a higher information gain. That means that we are going to calculate the entropy of the data set, and then calculate the information gain of each feature, and select the one that reduces the entropy the most. That means that when we get our data set, okay, we are going to calculate the entropy of the data set, then we are going to get a feature and see how this feature separates the data. Then we are going to calculate the entropy of the subsets to see if, when I select a feature, it reduces the entropy of the data set. Okay? Questions? How do we calculate the entropy? If we have a data set with 2 classes, positive and negative, that's our case, okay? The entropy has that formula, so minus P1 log 2 P1 minus P0 log 2 P0. And P1 is the probability of observing the positive class, so positive divided by all the instances. And P0, the probability of observing the negative class, right? Negative divided by positive plus negative. So entropy value is close to 0, low entropy, means that data are nearly concentrated only in one value. And close to 1 or higher, in our case here, because we have only 2 classes, the higher entropy will be 1. But we can have higher entropies, okay? So higher entropies means that data are spread as much as possible in its possible values. So we cannot conclude anything with a high entropy. High entropy means confusion in data. Low entropy means certainty in data. Okay? Oh, yeah.
But entropy is calculated only for categorical outcomes, or can we have like continuous instead of positive and negative?
No,
or
we
do
can't.
We always need classes.
We can calculate. I believe we have to choose other kinds of. Let me think. Other kind. Yeah, we have to think in other kinds of calculations because entropy is focused on the positive and negative class, on the categorical classes. So you can think. We have to take other measures. Okay. Okay. So let's see how we calculate the entropy for the entire data set. Okay, so we get the entropy value, okay, for the whole data set I showed you in the beginning. So if we look at the data set, we are going to see, let me go back to the data set. If we look at the initial data set, we see that we have 5 instances, okay, that make success and 5 instances that don't make success, okay? So we have 5 positive instances and 5 negative instances. Okay, good. So let's go back to our calculation here. So the entropy for that data set is calculated in that way. So P1 is 5 divided by 10, okay, 5 positive divided by 10. So half, and P0 negative, 5 divided by 10. Okay, so 0.5 again. So the entropy is minus 0.5 log 2, 0.5, minus 0.5 log 2, 0.5, and that results in 1. That's the highest entropy for this data set. Okay, the highest entropy as possible. I have 0.5% of the instances belong to one class, and the other half belong to the other. Half of the instances belong to a class, half to the other, okay? So the data set has its maximum entropy, the same number of instances for each class. We want to reduce that. We want to choose we want to choose a feature that reduces this entropy. So we have to calculate the information gain for the features. The information gain of a feature is the expected reduction of the entropy when we choose that feature. Okay? So in our example, the information gain of each feature is given by, see, the entropy of the whole data set, entropy of S, minus what we will call here the remaining entropy when choosing the feature country. Okay? So it's the same thing for all the other features. So the remaining entropy is the expected reduction in entropy when I choose a given feature. Okay? And we are going to select the feature that gives the higher information gain. So think about it. If we get the whole data set, the feature, the entropy is very high. Okay? when I calculate the entropy after choosing a feature, if this value is very low, then we are going to have a high value subtracting a very low value, resulting in a high value. So information gain will be high, we choose this feature. Okay? So a feature, generalizing now, a feature with D distinct values divides the training data into D subsets, okay? So each subset has positive and negative instances. Okay, so the remaining entropy for a given subset is calculated the same way we calculated an entropy. So we are going to calculate the entropy for each of the subsets that result from the division of the entire set after using a feature. So we use a feature, it results in, I don't know, P subsets. We calculate the entropy in each of these P subsets. We are going to calculate this. Okay. And after calculating the entropy in all of the P subsets, okay, we are going to okay, we are going to sum all of them. We are going to sum up all of these entropies, okay, together with getting a division of the instances that belong to that subset divided by all the instances.
When you are multiplying by this division, you are trying like normalize or give more más peso, more height to one feature than another, because if you have more pk and nk, you're going to have a bigger percentage of this remaining entropy, or no? It's not like that.
No, after calculating information gain, you can think that you are giving more importance to a feature than the other, because the higher the information gain, the better the feature. Okay?
Okay.
Yeah, okay, but you got it, yeah? You know, pk and nk are the positive and negative instances that are in a subset resulted for the division. Okay, and P and N are all the positives and negative instances in the subset here, in the set above here, before the division. Okay, good. So the information gain, then we are obtaining this with this formulation. So after getting the remaining entropy of a given feature, this remaining entropy is just the summation of all the entropies of the subsets after dividing the initial set using a feature. Okay, then we subtract the entropy of the whole subset from this entropy of in the feature. Entropy after selecting the feature. So let's do some examples here that's going to be more easier to understand, okay? So I'm getting again the same data set from the beginning of the slides, okay? And we are going to select a given, we are going to test all the features, okay? So if we select the feature country, let's see what happens, okay? Here. So with the feature country, see, we have all the subsets in the division. Okay? So, if we get the value USA for the feature country, here we have 3/4 of the positive instances and 1/4 of the negative instances. Okay? 3 positive instances and 1 negative instance. So we can calculate the entropy of this subset here, resulting from the value of country being USA. Okay? So minus 0.75, log 2 0.75, minus 0.25, 1 divided by 4, okay? Log 2 0.25, and we have that result, 0.811. Okay, so save that number, 0.811. Now we are going to do the same thing with this subset here. Okay? So in this subset we have 2 positive instances and 2 negative instances. Okay, so the resulting entropy of the feature being equal to entropy is like 0.5 log 0.5 minus 0.5 log 0.5. That results in 1. That makes sense because in this subset, I have 2 instances for each class. So it's a totally mixed subset. I cannot make any decision looking at that. So it has the higher possible entropy here in this case. The highest possible entropy. And let's do the same thing here now. Here, okay? So we don't have any positive instance, and we have 2 negative instances. So it's minus 0 log to 0, minus 1 log to 1, that's equal 0. So the lowest possible entropy. That makes sense because we have instances that belong to only one class. Okay? Now we have the 3 values of entropy calculated for these for these 3 subsets, okay? And now we are going to sum these guys. Okay, so the remaining entropy for the feature country is 4 divided by 10, the entropy we calculated for USA. Why 4 divided by 10? Because we have 4 instances here. Remember, pk and k, p1k and 0k, p1k and 1k. Okay? Divided by the total number of instances. This total number of instances are all the instances that belong to the subset, to the initial set, okay? So it will be 4 divided by 10, 4 divided by 10, 2 divided by 10. Okay, multiplied by the corresponding entropy here. 0.40811, 0.41, 0.20. Then the remaining entropy for the feature country is 0.7244. Okay, so save this number. Now to calculate the information gain for the feature country, we have to take the entropy for the whole data set, that's 1, minus the remaining entropy that we just calculated for the feature country, that's 0.7244. So the information gain for the feature country is 0.2756. Did you get it? Okay? Okay, so save this number, because we have to do the same thing now for the other features. Okay, so think about it. If we have a data set with 100, 1,000, I don't know how many features, we have to perform this for all the features. Okay? Good. So now let's make the things a little bit faster because we know already how to calculate, okay? So if we get the feature star, okay, using the same calculations, we can conclude that the entropy, if we choose the value yes, is 0.9852. And the entropy, if we choose of the value no, is 1. That makes sense, because if we look at back here on how the star divides the data, see here how the star divides the data, you see that it divides the data, the resulting subsets are not that pure. So you have a very high entropy here, and also a very high entropy here. Okay? Ooh. Ooh, 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 here. Oh, no. I just jumped. Oh, I'm going forward. Sorry. Entropy. Yes, here. Okay. The next one. And the next one. Yes. So the remaining entropy for a star is 7 divided by 10, because we have 7 from the positive side. Entropy for yes. Plus 3 divided by 10, because remember we have 3 from the right side here, 3 instances that have the value null for the feature star, okay? So 3 divided by 10, entropy for the feature star, for the null, okay? So you have 0.7, and this plus 0.3 times 1, you have this value, okay? So the information gain is 1 minus the remaining entropy for a star, that's 0.01. So this is the information gain for a star. And now we are going to do the same thing now for Geiger. Okay? So the entropy for Geiger, if we choose the value comedy, okay, is 0.918296. For romance is 0, and for fiction, science fiction is 0.918296. Okay, so again, because we have 6 instances here, mixing positive and negative, okay, so we have 6 divided by 10, entropy of comedy, plus 1 divided by 10, entropy of romance, plus 3 divided by 10, because we have 3 instances here, times entropy of fiction. This results in an entropy value of 0.82, that value there. So we have a remaining entropy for Geiger equals to 0.8264664. The information gains given by the entropy of the whole data set minus the remaining entropy, which is the entropy for the feature Geiger. So the resulting information gain is 0.17. So you see that information gain gives the reduction of the entropy. So in this case, I am not reducing the entropy a lot. In this case, I am not reducing the entropy a lot. But in this case, I am reducing the entropy. Okay? See? Now, so which feature to select? If we look at the data set, now we have tested all the 3 features, and we have to look at the information gain of each feature. What is the feature with the highest information gain? The feature country. Then we are going to choose the feature country to be used, okay? Because it has the higher, it has the highest information gain, okay? So this is going to be the feature that we are going to put in the root of the tree, the first feature of our decision tree. Okay? Questions? Now we have to repeat this whole process for all the other subsets, all the nodes that were generated. So we have the decision tree, we just started inducing the decision tree. So this is the first part of our decision tree. Now we have to repeat this process we just did with these 2 subsets. Okay? Now we have to consider this set here as if it was the entire data set. So we are going to compute the entropy of this guy here, and then we are going to choose a feature to put here, see how this feature divides the data, then calculate the entropy of each part of the division, sum, okay? Then get the entropy here, divide, and subtract the entropy we find here, and we have an information gain here. So we have to repeat this process for each subset. So if we look now at this tree, okay? A detail, of course. In this In this leaf, this can be considered a leaf node. Why? Because it's already pure. So we don't have to divide it anymore. So this is our initial decision tree. Now we have to choose which features to put here and here. Okay, so let's take a look. Let's take a look here. Let's first try to select which is the best feature to be put here to divide this subset, okay? We're not going to do the calculations because we already know how to do the calculations, but we are going to use our intuition, okay? If we select the feature star to be put here, okay, the feature star will divide this set in these two subsets, okay? If we select the feature gainer to be put here, it will divide this subset in these two subsets. 3, but 1 is empty, okay? So which one will give the highest information gain and the lowest entropy? Star, of course. Then star will be the feature that we're going to put here. Okay. Now we are going to do the same thing for the other subset. So if we look here in this remaining subset, if we choose the feature star to be put here, okay, the division will result in these two subsets. If we choose the feature gainer to be put here, so the resulting subsets will be these. Which feature gives us the highest information gain? The lowest entropy. Feature gainer, okay? Because it results in more pure subsets. And that's it. So we have our decision tree induced.
Before the class, I thought that like you should apply the same feature division by all the samples, all the nodes, but it looks that you can choose by node, right?
I don't know if I understood your question. You mean that that I should have tested country again?
No, like if you, in my mind before, like if I choose a star for one, I need to put a star in all of those. So you can choose one by one.
Yeah.
And then doing this one by one, how can I know like what feature is more important to division? Or
the feature more important to the division? No. You see, the position of the features in the decision tree is not related to the importance of the feature.
Okay.
No. To calculate the importance of the feature, okay, we are going to do this with another algorithm that we call random forest, that we are going to see here. And with this random forest, we can calculate the importance of the feature. But you can use in a tree, calculate its importance. You can do the following. Follow me. Let me go back here. Let me go back to the data set here. Here's the data set. Now you have that decision tree, okay? We have constructed, you have the decision tree ready, it classifies instances, it's okay. You can calculate the importance of the feature if you do the following. Take the data set, okay, and mix all the values of a feature here. For example, take the feature country and mix all the values, but only for the feature country, the other remains the same. You mix here. Now you test the decision tree with the data set with the mixed features, okay? If the performance, you mean accuracy, for example, of the decision tree decreases a lot, then it means that this feature is important, okay? If you mix the values and you test the decision tree and the accuracy is not so different as compared with the accuracy that if you were using the data set without mixing, also that feature not that important for the tree. Did you get it, what I mean? Mm-hmm.
Can you also test the importance of the feature trying, instead of mixing and try to excluding it, and see if the tree changes or not?
Yeah, but if you exclude the feature, then it will not be possible to test the decision tree, because the feature is there in the decision tree. If you exclude the feature from the data set, how you are going to follow the path in the tree? For example, you exclude the country. How can you test to decide which path to follow in the tree?
Oh, no, so if we had another question, in this case, we know country is important because of the information gain. But if we didn't know, like, for example, the first one, the star information gain was very little, 0.01.
Yeah.
If we try, one could think, oh no, the information gain is so little that maybe I didn't have to collect this information. Can we try to make a tree without it? Make sense?
No, you can have a tree. Your final tree doesn't necessarily have to have all the features of the data set.
Because I'm thinking, for example, with data sets like, for example, 100 features, maybe we don't need to work with all of them. We could exclude some.
Yeah. But how to decide what features to put in the tree? The information gain will give you that. And the stopping criterion that you are going to use to stop in constructing your tree. Okay, so for example, my stopping criterion can be, 10 instances in a node. If I get 10 instances in a node, then I will not divide that node anymore. Okay, so given the stopping criteria, after I stop inducing the tree, constructing the tree, okay, many of the features will not be in the tree. So these are not considered so important for my problem. Okay.
I have a question here from people online.
Oh, okay.
And he's asking if this grid algorithm will give us the best decision tree or just a sensible choice.
Yeah. The algorithm is deterministic. So every time you run this algorithm, it will give you the same tree because the data set is the same. Every time you run it, will give you the same tree. So it's the best tree for the data set we have. Considering the measures we have, yes, it's the best tree. However, okay, we can try to make random samples, random subsets with the data set we have and construct different trees. So in this case, we can have one tree that's better than the other. Then we have to test these trees to verify the accuracy of these different trees. Okay, we are going to do this when we work with random forest. We are going to construct a forest of many decision trees, and each of the decision trees will be constructed with a random subsample of the original data set. Then you see that with this random subsampling, you have different trees. Okay? And because the process of choosing a node, choosing a feature is deterministic, you are going always to select it. Using the calculations, you are going always to select the same feature. Okay, so because I do now random subsampling, I can have different features, and I can make the subsampling also randomly selecting some features to construct another data set. So I increase the chance of having different trees, and then I can evaluate them all and choose the best. But the idea in this case is that many weak trees together are stronger than one stronger tree. Okay.
Is there something like a delayed gain of information? For example, if I choose a feature that initially is not good to separate between success and failure, but the next one could be a good one that gives you a lot of information. This is possible? I don't know if you understand my question.
No, say again, please.
Okay. The idea is that, okay, I select one feature first, okay? And the feature is not so good. But it produces some data that can be separated better in the next selection.
Okay. Yes, this is possible. Okay, yeah.
Okay. And this is the idea that the random forest wants to capture?
Mhm,
or
yes.
not? Okay.
Yeah, you see that if I had the whole data set, okay, for sure I would select the best feature to be put in the root of the tree.
Okay.
Now, if I make a random subsample of this data set, maybe this best feature is not in my subsample.
Okay.
And then it will not be selected.
Mhm.
But that means that I can select another one that you said. I can select one to put in the root, that's not so good, but that results in a better separation further.
Okay.
That can happen, yeah.
Okay.
Questions? More questions? Yeah.
There's a way to do something like the decision trees, but using numerical data inside of categorical?
Numerical data, yes, we are going to see how to do that, okay? And actually, I'm going to use the board now. How can I change here? Note on? Cam off. Okay. So, okay, suppose you have a feature F1, okay, and this feature F1 has many values. I'm going to put here 1, 2, 3, okay, 4, 5, 6, 7, I mean, many values, okay? So each row here is an instance, okay? So what you have to do in this case is to make cuts here. So first, I'm going to test if feature 1, okay. Okay. Yeah, first I'm going to test if the feature 1 is lower than 1, higher than 1. Did you get it? Okay, then I make the calculations. Okay, then I have to change this and put here. And test if feature 1 is lower than 2 and higher or equal to. See? Then I have another division. Then I go make a lot of divisions. Okay.
But this will be done by the algorithm itself. You don't need to pre-state this range.
Yeah, the algorithm will perform that for you. If you use any package, yeah, it will perform that for you. But if you do by hand, by code, you have to test all the possibilities. Because here you are choosing the best split in data, the best division, okay? You know, you got it? Is it okay? Okay, so I can go back. Now I have to, oh, we're another question, sorry.
Sorry. What happens if in the beginning my target feature has more than 2 categories? So
more than 2 categories is the same thing, okay? You compute for the probability of that category, log 2 probability of that category, plus probability of the other category, log 2 probability. If you have K category, you just go summing.
Okay.
Okay? More questions? Now I have to press the same button, right? Note off, cam on, cam off. Okay. Oh, yeah.
Yeah, let me show you. Here it's only the slides, and this is the slides with a board.
Yeah, I know, I understood.
And down is the opposite.
Good, thank you. Okay. We just repeated the process, okay? We have our final decision tree, and now we can apply this decision tree to new data. Okay, so now suppose I have that new data, move 11, 12, 13, okay? I have the features. I just have to apply the instance in the decision tree and follow the path given by the features. So if movie is equal to USA, oh, that's in Portuguese, sorry, USA, and star is equal no, then the move is not make success. If move is USA and star is yes, move USA and star yes, then the move will make success. And if the country is other, then the move will not make success here. Okay, that's easy. Okay, but what if we have now, see the regression trees, you know, someone asked, right? How do we induce a tree if we have our target value? It's not a target, you mean, it's a real number, okay? What if you want to perform regression, okay? So in the simplest case, the leaf nodes of our tree will contain some instances, then we get the values, the numeric target values of each instance, and we make the mean. Okay, so in the simplest case, each leaf will contain the mean values of all, the mean value of all the values that, all the outcome values of the instance that fell in that leaf. Did you understand? Okay. What I can do also is to fit a linear model with the instances that fell in that leaf. So I just fit a linear model just like we did in the last class. Okay, we get the instances then that leaf and fit a linear model. Okay, then this mathematical function that can be the mean, a linear model that predicts the value, the target, the numeric value of my instance, okay? So if I have, for example, this regression tree, this data set, okay? And we have all these numerical variables here, and I want to predict, for example, the consumption. So suppose this is a car. Each row here is a car with its potency, weight of the car, the acceleration, and we want to predict the consumption in terms of fuel of the car, okay? So at the end, we can have a decision tree just like that, okay? And here, the leaf nodes, they can contain the average of the consumptions, considering all the instances that fell in the leaf nodes, or we can get the instances that fell in each leaf node and fit a linear model. Then to classify these instances, we just get the linear model and apply in the instance that fell in that leaf node, okay? When testing, we just follow the path like we did before. Then the instance falls here. We get the linear model and use it to predict the real value for that instance. Okay, questions? See? In each leaf, we can have a linear model just like that.
So these linear models will be in the terminal leaves of the tree.
Yeah, in the leaves.
Okay.
There are no terminal leaves. Leaves and terminal leaves are the same thing, because if you are at the end of the tree, they are leaves.
Little branches.
Yeah, you have just internal nodes and leaves.
Okay. Okay.
The leaves give the decision.
Okay.
The internal nodes the tests.
Right. Thank you.
So if I want to predict like a new observation, I get the values from the new observation, run through the tree, and then apply the linear model.
Yeah.
Okay.
That's it.
I guess like the geometric intuition for what we're doing in this case is that like we want to somehow separate the space of points in some high dimensional space, and then you're building like this piecewise linear manifold or whatever that separates, right, these points.
Mm-hmm.
So I guess the question I ask is going back to what we were discussing last class. How do we, in a thing like this, avoid overfitting, right? Because if I have a very large amount of variables, I guess I can construct any curve by piecewise linear.
Yeah, that's a very good question. We try to avoid the overfitting doing what we call pruning. That's one of the things we do to avoid overfitting. So, after constructing the tree, so let's get back here to the tree. So let's get this tree. After constructing the tree, we can do the following. We can get the tree and evaluate it in a validation data set, for example, or even the training data set. Then what we do the following, we cut here a branch, remove here, okay? And then now this one is transformed in a leaf node, because we remove it. All the instances here are transformed in a leaf node. Then we test it again and see if the performance decreases. If it doesn't decrease or if it increases, then we remove this branch. And we do this until the performance decreases. Okay? So this is called the post-prune. But we also can try to prune the tree while inducing it. So with this we avoid having very, very huge trees. And also we can put some stopping criteria. So for example, we can increase the number of instances that, we can increase the threshold that we use to split a node. So for example, we are going only to split a node if that node has, 50 instances. Okay, 50 instances or more. Okay, if it has less than 50 instances, it's going to be a leaf node. We are going not to split it anymore. Because the more we split the tree, the more you are, you can have overfitting. The more you split. The more splits you have, the more overfitting you have. That's why we have a factor of complexity. I'm going to go back here. Cam off. Now I'm getting it. Okay. Let's see if I remember. I can have here a summation of the error, okay, in each leaf, and I can sum this with a given factor here, multiplied by the number of splits. These are the splits. Okay, so the more splits I have, okay, higher I'm penalizing the error, And this is controlled by this, what we call here, it's a parameter for a complexity factor. So the higher this value here, the more I am penalizing the error. So the algorithms use this formulation in order to control how they are splitting the data. So the more splits, the more I am penalizing the data. Then I can memorize these values here, these complexity factors, for all the levels of the tree. Okay, compute the error for all the levels of the tree, and then after inducing the tree, I can choose the factor that results in the tree with the highest accuracy, and then I prune the other. I use this factor to prune the tree. Okay, so all the branches below that level I just cut. This helps to avoid the overfitting.
Sorry, I understood that for every leaf you can get a linear model, yeah. But the coefficients are associated to this part as well, to each linear model.
Yeah, we can get all the variables that were used for the instance to get there. Okay, and then we can fit a linear model using those variables.
Can you
yeah, for example, if you have the decision tree, then you have the branches of the decision trees, and you have a leaf node here. Okay, so this is a feature, this is a feature 2, sorry, feature 1, feature 2, feature 3. Then you have a data set here, and you have these 3 features for the data set. Okay, then you have to just fit a linear model using these 3 features. Okay, or you get the average, right? You can get the average, I don't know, you have, for example, 50 values, 50 instances they found this leaf. Okay, then you get the outcome. Oh, my letter is terrible. Then you get the outcome of these 50 values, and you take the average. That will be your prediction.
Why the entropy formula is defined in terms of logarithm base 2?
Yes.
Yeah, but why we need to apply that base? I mean, why is not 10 or natural logarithm?
I don't know if I think I don't know how to answer that question.
Okay.
I don't know.
Okay.
I think it's because of the formulation in terms of getting a value of 0. I'm not sure. And getting a value of 1 in the binary case, you get a value of 1, the highest possible, and 0 in the lowest possible. I'm not sure. Sorry. More questions? Okay, so let's do some coding on this. And now I have to go back to my computer. Yeah. You already have the codes, right? Opa. Okay. So, where are my codes? Here. Is it okay for you to see? Okay. So, we are going to work with that data we just worked before, right? So I'm going to read here the data we created in the last class. Okay, with the read.csv, and I'm just showing here part of the data. So, as you can see here, there are missing values in this data. Okay? What I am doing now is to use that function, remember that function, that we constructed to input missing values, right? I am going just to apply the function in all the columns of my data. We did this yesterday, okay? Now I don't have any more missing data. Nice. We are going to do the classification with this package, okay? If you don't have it installed, you have to perform an install packages and put the name of the package. Okay, I already have the package installed, so I don't have to install it. Is it okay? You could load the package? Good. Now I'm going to divide the data into training and test data sets, okay? So I'm setting a seed here in order that everybody can get the same partition. Okay, I already explained this to you yesterday, remember? I am just sampling numbers 1 and 2. I have 7% of getting the number 1 and 30% of getting the number 2. Okay, then I am indexing the training data using that vector composed of true or false values. Okay. Well, okay. Now here, I am constructing a formula. I need to get a formula here and pass to this function C3 to induce a decision tree. Okay, so I'm saying here that I'm going to use all the features against the target feature. Okay, then I'm inducing a decision tree here, saying, okay, do all these calculations I showed you, considering that the target is the feature. Okay. Just one thing, because this is a numeric target, remember? Let me see. Conditional inference trees. See, here you have all the options that the test the global hypothesis of independence between input variables and response. I wanted to check here if it uses Gini. Yeah, I'm not sure. Anyway. Okay, splitting the data now induces here the tree. Okay, and interesting now we can plot the tree. See, here is our decision tree. Okay, so it gives here. And interesting, differently from the algorithms we saw yesterday, when we use the decision trees, we can work with categorical features. So you see that I did not use here the one-hot encoding. I just worked with the categorical features, okay? So this decision tree is telling me that if the SNP26 is G, then 271 instances fell here in this root node, in this leaf, okay? And this Y here is the prediction. Probably it is the average of all the target values of the instances that fell here in this leaf node. Okay? And the same thing for the other leaf nodes. Good? Now I can make predictions in the test data set. See, I just use this function predict, passes here the SNP tree, and says that the new data is going to be the SNP test. I'm constructing here a matrix where I am concatenating in each column here the true values and the predicted values. I'm putting a name in the columns and showing the matrix. See? And see how interesting. Because this tree is small, we had 50 features, but only 4 were selected to be put in the tree. See that we have almost the same value being predicted by all the instances. And sometimes it changes. Okay? So this is a good example of the bias variation trade-off, okay? If I have a tree with a variance, if I have a tree with a high variance, this tree will be much higher, much bigger, okay, with a lot of nodes. Then probably the outputs of the tree will be more diverse. Okay? So this tree can be good or can be bad. That depends. We have to evaluate it. Okay? Okay, nice. Let's go into evaluate here. I am computing the root mean square error, okay? I'm just getting the true values, subtracting from the predictions, okay, calculating the square, dividing by the number of instances, and then taking the square root. So this is the root mean square error. Here's the value. Easy? Okay. Now we are going to use another package that's more specific for doing regression. Okay? If we take here the, let's see if the help gives us something, R part. Recursive partition in regression trees, more specific for regression. Let me see aqui. It uses more or less the same thing we saw, but a little bit different. Each package you use will give a different calculation, but the idea is more or less the same, okay? Getting a data set and choosing the best feature to split that data set, resulting in more pure values, okay? So let's use this R part package, okay? So the same thing here, I have a formula, and I am inducing a decision tree, saying that I'm going to use all the features against the target to predict the target here. The data that I am going to use is the training data. And here I am passing a parameter that's saying that the minimum number of instances in a node for this node to be split is 10. Okay? If I have less than 10 instances in a node, I'm going to transform that node in a leaf node. I'm not going to split anymore. Here, and I am showing the tree here. You see now that I have a much more complex tree. See? I can plot this tree with this package rpartplot, and see here, I have a much more complex tree. And just to see how the data set, the splitting data set in training and test samples can influence the tree, let's change here our seed. Let's go up there. Let's change our seed here. And let's go back to our tree. Now I have a smaller tree. See? It's a smaller tree. So the subsets I performed, the way I make subsamples, I divide the data in training and testing, that influences the tree I am constructing. That's why it is so important to do that k-fold cross-validation I showed you yesterday. Because you more statistically validate the model you are constructing. Because sometimes you construct a model, then you test that model in test data, and then you say, whoa, it's a very good model. But sometimes the split you make in the data favored your model in that occasion. That specific split was good for your model. So you have to do a lot of different splits, okay? So just to show you a prune strategy, I'm going to go back to my original seed. Construct the decision tree again. Okay, plot it. Good. Yes, there it is. Okay. So I'm going to do the following now. I'm going to prune the tree according to that complexity factor I explained to you. The more splits a tree have, the more complex is that tree. So I can use that complexity factor that's calculated to choose in which level to prune the tree. I'm going to cut all the nodes from that level below, okay? So with this table here, with this parameter, CP table, I can see a table here with this, the number of splits, okay? The error, the relative error of each node, okay, averaged over each nodes, when I increase the split. So there is a tendency to see that the splits, the error decreases, okay, when as the size of the tree increases. But occasionally the error can increase, okay? Yeah, in this case I'm not going to be able to prune because you see that the smallest error is the one that's associated to the last split, okay? But we can try to find here, just to give you an example, a tree, well, a tree that results in a higher error that I can split. Let's do again here, another seed. Whoop, where is it? Here. Again. Oh no, it's not this one, it's this one. So let's see here. Yeah, it's still decreasing. Yeah, but just to show you, okay? Now suppose that, okay, let's suppose, okay, let's give him one more try, okay? 53, one more try. I don't know, any seed here. Let's try to induce again. Let's give one more try. Yeah, it's going to be difficult. You know, but suppose that I want to prune this tree, the tree in this level. For example, I don't know, 46 to 45, I don't think it's a sufficient reduction in the error that justifies the size of the tree, okay? I want a less complex tree. So what I'm going to do, I'm going to cut this tree in this level. Actually, I'm going back there to see the effect of the tree. I'm going to go back here in the seed that I used, 1, 2, 3, 4, 5. I'm going to run again. Here, okay. So you can see here the table. Okay, so look here. Okay, let's see. I'm going to cut here. I'm going to cut here, okay? So what I'm going to do, I'm going to get the complexity factor here, SNP3, CP table. I'm going to get the complexity factor here on the level, here on the level 6. So this is going to be the value 0.0119 here, okay? Let's suppose I see the decrease in the error doesn't justify a tree that's so complex. So I'm going to prune the tree here, okay? So I'm going to get this guy here. Okay, I'm just I'm just comment this code here. I'm going to put all pt equal to 6, because this code here gives me the line corresponding to the minimum error. Okay, but the minimum error here will be the last split. But I don't want that. Okay? I want the level 6 to prune the tree. So here with this code, prune, I'm getting my tree, this tree here, and I'm saying, look, cut the tree, okay, using the complexity factor corresponding to the line 6. The complexity factor corresponding to line 6 is this value here. Okay, this value here. Then I'm going to cut the tree in the level 6. And then I'm going to show here the tree again. See, I'm here, I have a snip tree pruned. It's another tree, okay? Here. So this is the tree that was pruned. And this is the original tree. Okay? We can compare the error of these two trees, testing them. Okay? Here. So I'm going to get, I'm getting the predictions using the original tree, and I'm getting the predictions using the pruned tree. Okay? Always using the same test data. And here I am concatenating, okay, the original outcome, the predictions of the original tree, and the predictions of the pruned tree. And I'm creating here a matrix. See? Pruned, original and pruned. Good. And now here, I'm going to calculate here the root square error. Okay, root mean square error. Considering the original tree, the predictions of the original tree, and the predictions of the pruned tree. Okay? And I'm just printing this here. Okay? And you see that, see, the error of the original tree was higher than the error of the pruned tree. And the pruned tree had a much smaller tree. The pruned tree is much smaller. So in this case, I am avoiding overfitting because I pruned the tree. Okay? And having I increased the generalization ability of the tree. Okay, questions? Any questions?
Is there a specific measure to optimize the data set that we're using based on entropy or something? I don't know.
Optimize the data set?
Yes. Because I know that there's this problem in artificial intelligence is that to use the right data set, like balanced and this.
Yeah, trash in, trash out, right? You need to use a good data set to have a good model. You can do you can perform a pre-processing. Actually, the pre-processing a data set is a very important step in machine learning. Okay? So, for example, verify if you have a lot of correlated features and remove the correlated one of the correlated features, not all of them, but one of the correlated features. Perform the imputation of missing values, but using a very good measure, for example, using correlation between instances. So instead of getting a missing value of a feature and, for example, replacing them with the mean, you get the more related instances to that instance that has the missing value. See, for example, you calculate, for example, the Euclidean distance, okay, between all the instances in your data set, and the instance that has a missing value. After calculating this, you get, for example, the 10 closest instances for the instances that has a missing value. And then you analyze if this feature has, for example, a normal distribution. If it has a normal distribution, you can calculate the mean of the feature for the 10 instances that are more close to the instance that has a missing value. So this kind of preprocessor is important for you to improve the quality of the model you are inducing with the algorithm. For some algorithms, for example, it's important to normalize data. If you are working with algorithms that use distance functions, for example, distance metrics, like, for example, neural networks. Neural networks, actually, you are calculating the distance of a vector of weights from your vector, your instance, that's a vector, okay? So because you're calculating the distance, it's important to normalize or standardize your data. Because if you don't do that, you have features that will be much more important than the others in the calculation, and that introduces a bias when you are inducing your model, okay? That's not the case of decision trees, because you are just comparing the values. You're not making any calculation regarding distances.
I got a little confused at the part of the pruning, because when you showed us that table where you see the error, and if it's decreasing or increasing, can you go back there?
CP table here.
Yes. And then you were looking to this, I suppose it must be the relative error, I don't know, the rel error.
Yes.
But in the code was calling the X error.
Oh, yeah.
And in the X error, indeed, you have a minimum error at row 5. The error decreases, and then it goes increases again. So what's the difference between these two metrics, and which one should we?
Yeah, this is actually, I think it's a very good idea actually to look at, to see the X error. This is a cross-validation error. It performed an internal cross-validation, and it presented the average error over the cross-validation. Yeah. So in this case, if you look at it actually makes sense to look at the X error, because you have an error that was obtained by making splits of the data internally, you know. So it makes sense, yeah, I should have looked at line 5, for example. And actually you see, because I pruned at level 6, now if you think, it makes sense that the pruned tree obtained a best accuracy than the original tree, because the pruned tree, okay, obtained a best X error than the original tree. Okay, smallest X error than the original tree.
Okay.
Nice, good observation. Yeah. More questions? Okay, I think that's it. We are in time. So after lunch, I'm going to show you how to induce a random forest. I'm going to show you actually how a random forest works, and how to use random forest and specific measures to compute the importance of the features. Okay? Nice.